Today's question, our pre-class question, is to think about what is orange and delusional and thinks it's doing great things for the world, but is actually doing horrible things and ruining people's lives. Does anybody know? No, you don't know. Chegg. I hate Chegg. Hate it. It tricks you into thinking, oh, I'll just check a little bit, it'll help me a little bit, and the next thing you know, you're not learning anything. And you get to pay $15 for this opportunity. Wow, a month. Horrible. I could go on for 30 minutes about Chegg and the people in charge of Chegg. I've looked up their backgrounds and everything. So do you want to hear the 30-minute rant about Chegg, or should we do physics? Don't tempt me! They have a chief learning officer that's never taught. A CLO, the world's only CLO. So not a single CLO has ever taught a class. So that pretty much makes sense. So let's see, why did I want to make fun of Chegg and tell me how much I hate them? Because the pledge problem is out. Yay, the pledge problem. So there's our first pledge problem, as you know. And I just want to stress, read the directions to the pledge problem, staple it neatly, turn it in. Came out yesterday. It's due next Monday. It's due at noon, not midnight. Right? Do we do that to be mean? No. We want to get it back to you. The quicker we get it, the quicker we can start the grading process and try to get it back to you by before the exam and time to look at it. We're going to try. So if we get it at noon, we can get it all cycled and handed to the graders on Monday rather than waiting for Tuesday. So remember, it's due at noon. It's basically one long problem. It's not as strict as the exam because you have a whole week to do it. Spend all the time you want. We recommend you sit down and try to take it under exam conditions. See if you can do it in 30 minutes, right? Because on an exam, you'll need about 30 minutes for each problem. So give it a shot. Try it in 30 minutes. And then put it away. Don't think about it for a while. And then come back and then spend another 30 minutes or maybe an hour kind of cleaning up your answer, maybe rewrite it, make sure you got it right. But it'd probably be worth practice trying to do it in a real exam condition. But keep in mind, all work should be your own, right? You cannot talk to anybody else about this. This is why it's called the pledge problem. It wasn't named after our first professor, Georgius Pledge or whatever. It's because it's pledged, right? It means you can't consult. So I think you know that about pledge problems. But maybe this whole class is just like a formality. We all have to do it. And no one really cares. As long as we all get a grade, move on with our lives. So maybe if you cheat, we don't really care. No, that's not the case, right? So don't think, oh, cheating, maybe I'll get a little help or ask Chegg. Don't do that. Don't do that. Right? We take teaching physics very seriously. You could say we've dedicated our lives to it, couldn't you, right? So if you cheat on this pledge problem, it's like you're making fun of my entire existence. And I take it personally. This is not a joke. Okay? So we take cheating very seriously in the Intro Physics series. Okay? And that's like the nice guy advice. I'm saying, this is important to me. I don't want you to cheat. I'd much rather you get an F than cheat and learn something, right? Now here's the threat. If you cheat, we will catch you. Okay? We're so good at catching people. You know why? Because people that cheat usually aren't thinking too well. Okay, so we have a lot of ways we catch people cheat, and it's usually of their own silliness. I won't tell you all the examples because, then you would know all the examples. But let me tell you one. One year somebody uploaded the pledge problem to Chegg, and they had their name on it. Right? So, So I think most people in the room aren't going to be that dumb and cheat. I'm probably preaching to the choir here. But yeah, don't cheat, because we will turn it in, and we will find it. I have had cases where I just flip through all the pledge or all the problems and just visually notice the two that are exactly the same. Right? So we have ways of finding these things. So of course you guys, I know, would not even think about it. But if you get a little tempted and your thought process goes towards, well, maybe nobody cares. We care. Right? So we send a few every year. Every year. Okay, so any questions about the pledge other than don't cheat? Uh-huh. Yeah, so it is. I'd say it's a little heavier on week 1 and 2. It has a little bit of force in it, but it focuses more on the kinematics. So we didn't really do that on purpose. We meant to have it more balanced, but it just ended up a little focused on the kinematics. But keep in mind, you're not limited in time, so you can look at it and think about it and go study before you take it. We recommend taking it in an exam situation, but you're allowed to study in all the book and all your homework. None of that is cheating. It's only working with someone else or going on the internet to get the answer that's cheating. Mm-hmm. Yeah, so explain all work means, so we would never want to see, even if the answer is just 0, right? What's this force? And it's just 0. You can't just put 0. So if something has a lot of equations to get there, that's a pretty good explanation. But if something is literally just everybody knows it's zero, so it's not moving, the sum of the force is zero, at least put zero. The force, it's not moving, acceleration is zero. Right? Put a teeny little bit, just because that helps us know you really did think about it. Again, it goes back to the cheating thing. It doesn't need to be an essay. Right? But they do want to see a little bit of the thought process. That actually helps you, believe it or not. Any other pledge problem questions? Cool. Okay, so you got a week. Let's see. So what we're going to do now is switch to, do I have to do this? Is this required to give for something? I don't know. So we're switching to rotational motion. So let's look at our new list of concepts here. Is it becoming funny? I don't know. Okay, here we go. So our new things we got to think about here. Uh-oh. This used to work this way. Here we go. I'm telling you, we're doing this poster thing. I don't care what it takes. If I have to hold it up, here we go. The holder is broken. We're going to talk about the kinematics of circular motion. Okay, that's basically what we're going to talk about. And let me just read from it. We're going to talk about the kinematics of circular motion. This is like notes for me in 10 years. This is how I'll lecture. So the kinematics of circular motion, the dynamics of circular motion. And you know the difference. Kinematics is how you describe motion, and dynamics is the force that causes that motion. So we'll talk about centripetal forces. That's going to be today, and then Thursday will be gravity, and how gravity causes circular motion. So if you look at the schedule of topics, you can see we're sort of covering a huge range and jumping all over the book, because we're sort of contracting a lot of things down. But we're giving you the critical important parts. Okay? Here we go. So let's talk about that now and get rid of this. Here. Oh, that was that one, of course. Yes, circular motion. And that is for later. Okay. Let's get rid of all this. Okay, so here we go. So normally, we would cover this longer. Can you put up the chart so I can take a picture of it? You can take a picture of it after. Normally, we might point out that we would cover these over a month. And I would be pointing out very carefully the exact differences between these things. And I'm still going to tell you, we're just not going to harp on it for like a week, okay? Or for weeks. So angular, circular, rotational kinematics. So underneath, I'm just going to put in parentheses, subtle differences. They're not exactly the same thing, but they use very similar mathematical symbols and concepts, okay? So in this class, we're going to do this for 2 weeks. So we're going to kind of blend them together a little bit, but I'll point out when we're getting to parts where they're kind of different. So the simple difference is we are turning rather, than translating. So all the kinematics we've done so far has been something translating in x, maybe both x and y, which makes a parabola. That's pretty much what we've done. So now we're going to actually turn things. So here is our wheel here, and here it is turning, and say this is the horizontal, like this is theta equals 0, so it's going to go like this, right? It's going to turn around and around. It's not translating anywhere. It's just rotating about a certain point. Okay, so let's draw that like that. My circles are better than Costanza's circles. And here is 0 degrees, right? And let's imagine this is just some edge point on that circle. Or this could be a wire and a bead is going around the wire. And for now, let's just say it goes in any old crazy kind of motion. We just want to talk about kinematics and how we're going to describe that motion. Well, that's what kinematics is, right? So we're going to talk about 3 parameters that you may sound familiar. The angular position. Before we had the position x. Now we have the angular position. Usually you can call it theta relative to wherever the origin is. Theta equals 0. Right? So if that's theta equals 0, then this is some angle theta from the center like that. So there's theta. So that's like position x. Theta, that. The units are in degrees or radians. Oh, we're going to talk about radians today. Hopefully you love radians already. 2 is angular velocity. So just like position, or just like something moving along, it can go through different distances in a certain time. This can go around different amounts in a certain time, right? And that is how fast around it's going, would be the simple definition, and we call it omega, right? The Greek letter omega, and it's equal to just d theta dt. So it's just like the other kinematics. Just like v is dx dt, omega is the equivalent d theta dt in, you can guess, radians per second. Okay? So in some problems, like when you're setting up a problem and talking about the angles, you'll often see it in degrees, but then when you go calculating something in omegas, it'll always usually be in radians. You rarely see degrees per second. So I can't claim we should always do radians or we should always do degrees. It gets very mixed up. So you just got to be good at going back and forth. So I bet you guys could think of the third one, right? Angular acceleration. So I'm not even going to define it. You know what it is. It's the time derivative of angular velocity. It's how fast the velocity changes. It is alpha. This is not the centripetal acceleration. We'll get to that later. This is the actual angular acceleration. Let's see, angular acceleration. It's d omega dt in radians per second squared. Okay. So there's the basics. So now we could spend a week saying, well, theta is theta I plus omega naught t plus 1/2 I alpha t squared. And omega final squared equals omega initial squared plus 2 alpha theta, right? So all those kinematics equations from translation copy over exactly to rotation. So we could spend a whole week on rotational kinematics, but we don't want to. It's boring. It's the same thing, just something going round and round. So what we're going to do is move on to more interesting things here. Get on with our lives. But I mostly just put that just to get the basic parameters in front of you. Angle, omega, and alpha are the rotational versions. Okay? So what we often do in physics problems is connect the rotational parameters to, and then the word to use here is very difficult to come up with. You could say translational, but that's not really right. Nothing's translating. What you mean is we want to connect that to how something is moving actually on the edge, right? So if I put this like red piece of tape on here where you can see it, now it's going around, right? And it's signifying one point of the edge of the disk. And if you think, if I look at it right here, I could imagine how fast it's going, right? It has a velocity. It doesn't just have an omega. If I count around how fast it goes around, that's omega. But if I get really tight on it like that, right, it has a velocity. So we have to connect the rotational parameters to what? To the translation of what? It has no name. I read a bunch of books. It has no name. I call it edge translational. I just made that up last night. I think it's going to catch fire. It's going to be all over Twitter. Edge translational. And what it just means is the translational motion of something on the edge. And if for a minute you imagine it's going straight on the edge, then it's our old things, velocity, etc. Okay? The other weird thing about this is when people want to talk about edge translational, as you'll be seeing by noon, it's going to be all over. Okay? It's classic. They're too excited. They have to get to omega. They're so excited about omega, they immediately define omega. And they skip the most fundamental thing in all of geometry, right? Which is the arc length. It's like if you did kinematics and you skip position, you just went straight to velocity. Well, we got to do the arc length, right? We got to do, this is basically the distance along really a curve, but we'll say the curve of a circle. We're kind of focusing on circular motion, even though we haven't formally said that yet, of a circle. Right? There's a formula to get that, right? So if we draw a circle like that, and it has some radius r, okay, and let's see, circle, radius r, and I go from here to here through some angle theta, then the arc length is literally this curved distance here along the edge. It's the curved distance. It's not this straight distance, draw a triangle in there. It's actually the distance along the curve. The formula, very simple, S equals theta r. yes, this is really just how we get the circumference. But circumference is kind of like a formula you memorized. There is a general version of this. The arc length around a circle is theta times r. Let's look at how the units work out. What is the arc length in? It's in meters. Right? It's a length in meters. And what is r in? The radius is in meters. So what could theta be in then? So theta is in radians. So it looks like your units aren't working. That's kind of weird. That's because radians aren't really like a physical unit. Okay, we use them for angle, but if you see radian on one side and not on the other side, it's okay, because it has no like physical meaning. Really, you could say this is in median raters. No, it's in MR, whatever the hell. You know what I mean? Anytime you have a curve length, you could say it's in meter radians. Okay, but you don't really need to because the radians don't really exist. You can just say it's meters and meters. Don't worry about the radians. Okay, so that's one little intro to radians. Now let's, just to show it to you a little bit better, let's say the S, by S I mean arc length, is a fraction of the circumference. Clearly, the circumference, is all the way around, so S is a fraction of that. So let's just calculate that. S is a fraction of the circumference is over 2 pi r. The other thing that's a fraction of the circumference is the angle. Right? So if we have the angle theta in degrees over 360 degrees is all the way around. Okay? So now let's turn this into the definition of arc length. So let's go to the definition of arc length and see what magical thing happens here. So let's see, this S, I'm going to take that over there and I want something times r. So what I'm going to end up with is theta in degrees times that pi went over there. The 2 cancels the 360 down to 180 times r. Okay. So when you're given a problem in degrees, this tells you kind of how to convert it to radians. You take the thing in degrees and you multiply it by pi over 180. Right? That's the conversion from degrees to radians. Because we know this number has to be that angle in radians. That's how this works. You can't have degree meters. You can only have radian meters. So if you have it in degrees, pi over 180, right? And that's why we have all these famous positions. This is 0 degrees and 0 radians, right? Therefore, 180 must be 1. So all the way around to here is 180 degrees, and it's pi radians. And this is 90 and pi over 2, and this is 270 and 3 pi over 2, etc. And then 2 pi all the way around, okay? So I'm just trying to give you some feel that radians are like real. They aren't just some made-up factor multiplying degrees. I mean, it comes from the definition of a circle in geometry and things like that. But don't panic if it looks like your units aren't balancing. See, this is why I hate dimensional analysis. It's one reason. Okay? Okay. So let's see. What we were doing is we had our 3 rotational parameters, and now we're coming up with our edge translational parameters. That's what we were doing. Believe it or not. So the first one was S. I didn't write it here. S. Yeah. And now we're going to do 2 more. Good Lord. Oh, it's stuck. It's stuck. Should I fix it in real time? This has never happened before. There's a first time for everything. Oh, it's really stuck. Boom. Yes. Okay. 30,000 a year, folks. Here we go. Let's see. Okay, so another edge translational thing we want to talk about is how fast is the tape going. Right? If I just zoom in right here, it flies by at some speed. So that's, of course, what we call the tangential velocity. Tangential velocity. And basically, it's the velocity along the trajectory. And it is like your normal translational velocity. It's in meters per second. We use v to describe it. If something is going around here and it's going in a circle, you draw it like that. V, and we'll put a t on it to tell you it's the tangential velocity, like that. All right, so this thing's here, and it's at radius r, going around a circle. So what is it? Well, if we want to calculate it, its magnitude would be ds dt. Right? How much arc length is that thing passing by per second? So let's do some calculus, ds dt. So we want to take the derivative of ds dt. Well, we look at s. And we say, d what here dt? Well, r is constant. That's just d theta dt. So it's d theta dt times r. D theta dt times r. Well, what is d theta dt? It's omega. Right? So the tangential velocity, if you want to write it in terms of the rotational parameters, you just take the rotational velocity and multiply it by the radius. That's pretty simple, right? That's how you get it. You're going to find that I promise you, remember I said the first 3 weeks is a lot of crazy, difficult vector math stuff, and then it'll chill out, right? So there you go. We have nothing that even has terms added yet, okay? The concepts now get more difficult, but the math gets a little easier. Now, often when we talk about this, it's often called the speed. So let's think, why would it be referred to as the speed all the time? And the answer is the direction is constantly changing. You wouldn't want to try to write this in vector notation because, well, right now it's pointing this way, but later it's pointing this way. It doesn't have a constant direction. The only thing constant is the magnitude, usually, if this is uniform motion. So if the magnitude is the only thing you can really characterize easily, the magnitude of velocity is often called speed. Okay, so in a problem, they'll often tell you it's going by and its speed is something. That's because they don't want to deal with the direction. They just want to give you the magnitude. Right? Okay, so VT is speed. Let's look at another one. 3 is the centripetal acceleration. That's fun to say if you've never said it before. Centripetal acceleration. How many of you have never raised your hand? No one. One. Okay, cool. Okay. Try saying centripetal acceleration as well. So centripetal means center seeking. So it's just the fact that this thing is accelerating. Now, which way is it accelerating? Is it what? It's in the center? Let's decide. So what is acceleration? A is delta v over delta t. If we give up the derivatives for a minute, we're going to go back to finite intervals because we're going to try to draw this. Okay? So here we are. It started out here, and it was going kind of that way, right? Because this velocity is always tangential to the surface. Okay? So that was at 1, and this was at t1, we'll say. I mean, it's a radius, but it's at time 1. And then later, it's going like, let's say here. This is where you capture it at t2, and it's also tangential. So that's v2. So there's your 2 tangential velocities at 2 different times. So what is delta v over delta t? Well, don't forget, that's v final minus v initial. I'm going to call it, I screwed it, v2 minus v1. I should have called it initial and final. But that's the difference, v2 minus v1 over delta t. So if we want the direction, we just have to do the vector addition of v2 minus v1. And how do you do that? You draw v2, which is pretty much down like that. And then you draw v1 head to tail, but you reverse the direction. So it's kind of like, why is that going to suck? Let's see. Oh, that's why. Yeah, it's kind of like that, right? So there's v2, and there's minus v1. So what's the sum of those is like that. That's v2 minus v1. You divide it by delta t, well, and you've got the acceleration vector. So it's the same direction as the acceleration vector. And sure enough, just from our little drawing here, you see it points in, right? Center seeking. So you can get the direction just from a quick little drawing of v1 and v2 between 2 different times, if you put them far enough or close enough together. What about the magnitude? The magnitude is not as clear. And we call it AC, the centripetal acceleration, and it's vt squared over r. Okay? I have a way I can derive it for you. It takes 10 minutes, and it's incredibly unsatisfying. Okay? So we're not going to do it. I have a video doing it, the least watched video on YouTube. And I'll post it. Maybe it'll get up to 3 views. Okay? But yeah, it's just you can get there with some little geometry BS, but it's really not, it's not very insightful. So let's not bother. Okay? Just trust me, the centripetal acceleration is v squared over r. So we have omega r here, v squared over r there. Okay? These are sort of a few standard definitions. We're going to give you more definitions soon, Because some of these are not what you would use in a problem. Like if a problem said calculate this, the tangential velocity, it probably wouldn't originally give you omega. It'll tell you like how long it takes to go around or something. So we'll show you how to do it with that in a little bit. I didn't write my name. Final or initial? Yes. I'm not sure exactly what the question was. Okay. Let's keep going, and these will become clearer. Okay, so now I've sort of been tricking you. We've kind of been talking about a specific kind of motion, and we kind of haven't. Okay? I keep drawing something going in a circle. I've maybe implied that the velocity was constant, but now I'm going to tell you. We're going to do uniform circular motion. This lecture is going way too smooth because I haven't written my number up here. There you go. Let's see. So the question is, does gravity affect centripetal acceleration? That totally depends on which way you're moving. But we're going to do some problems like that before this lecture is over. Why is it v sub t in the acceleration formula? Because in general, it's because v1 and v2 is a constant magnitude. Right? If we're now doing uniform circular motion, v1 equals v2 magnitudes, and that magnitude is usually called vt, the tangential velocity. You don't have to write the t every time, as long as you know what it is and don't get confused. Okay, uniform circular motion really is the motion I've been drawing. It's just constant vt. Right, the magnitude of that velocity is constant. I didn't say it was, I didn't say it wasn't. Kind of implied that it was. Right, but now I'm saying if it's really constant, that's uniform circular motion. Right, so let's look at some uniform circular motion. Here we go. See the little red dot? Here it goes. Uniform circular motion. Is it perfectly uniform? Not really, because it's slowing down, isn't it? I can't make it perfectly uniform. What is the W in the equation of tangential velocity? That's omega. That's omega. Because over here we said at the very beginning, angular velocity is how fast around is omega. So it's a lowercase omega. Uppercase omega looks like that. Lowercase omega looks like that. If I draw a W, I draw it like that, except I go really fast and I draw it like that. So you can't tell. I try to make my omegas very loopy. And I just don't draw W's in general. Not that kind of guy. So uniform circular motion means the velocity is constant, and it also means, one way to think about it is the centripetal acceleration is the only acceleration. We'll talk about cases where something is not in uniform circular motion, and it's because some other force is messing with it. Like here, friction is messing with it, and the acceleration is not exactly centripetal. But for now, uniform circular motion, it's centripetal. Here we go again. Something going around some circle with radius r. It's going at some tangential velocity that's constant. We don't need to put the bars on there. And it's got some centripetal acceleration coming in. Okay. What we're trying to do is build up more and more parameters to think about. We're almost done. So we had those three: position, theta, omega, alpha. Then we have these three: arc length, tangential velocity, centripetal acceleration. That's really all you need, except problems often give you the period. Period t. T is the time for a complete circle, a circle. In s. That's s for seconds, right? It's in seconds. So a problem will say this thing goes around in 30 seconds. That's the period. So we want to show you the formulas with the period in them. Okay? They might, it's less likely that they'll give you the frequency, but they might. And that's just basically, in this case, it's circles per second. How many? The number of circles per second. And it's in hertz. And hertz are 1 over seconds. So, and it's big L, it's little f. So the simple relation is just f is 1 over t and t is 1 over f. Okay, but usually these are really the exact same information. Okay, they're not different. So we'll say that f equals 1 over t. And we'll send that's a formula, but I'll point out that this is not some fundamental property of the universe. This is the same info. It's just a problem might give you one or the other. That's all. Okay? That's not the important thing I want to show you. What I want to show you is how we now write these in terms of this thing that most problems are written in terms of. Okay? So instead of this calculus-based tangential velocity where we took a derivative of the arc length, which is a little unfamiliar, for uniform circular motion, let's just calculate it, right? It's how far it goes over how long it takes. So how far does it go? One circle is all the way around, also known as the circumference, also known as 2 pi r. And how long did it take? It took the period. So that's another way to figure out the tangential velocity. In a problem, if you're told how big the circle is and you're told how long it takes to go around, then you just imagine it going in a line, and it's just delta x over delta t. And if you notice, if you're really paying attention here, you say, wait a minute, look at that. What is that? What was 2 pi over t? That must be omega. I know that's omega, for one thing, I know that Vt is omega r. Right up here, Vt is omega r. This thing must be omega. And does it make sense that that's omega? Yes. Because it's basically going through an entire 2 pi radians, an entire circle, and how long does it take? It's the radians per second. Right? So you can see it's sitting right in there. Okay. So you can see then what we've said is Vt is omega r. Well, we already knew that. Right? That's from calculus. So you get the same thing. And then again, the centripetal acceleration I'll just give you. We won't prove it. Oh, we could just substitute here. Right? If Vt is omega r and the centripetal acceleration is Vt squared over r, then it's omega squared r squared here, and one of the r's goes away. So it's omega squared r. Yeah. The centripetal acceleration there. So that's really all these are just new relationships, right? The new values you care about are the period and the frequency. And these are some relationships between them. And a lot of these relationships are redundant, like I said. I mean, saying this is the same as saying that. It just depends on what problem you're doing. Do you have the period, or do you have the angular velocity? Okay. Let's see. Now we're going to do a sample calculation in our final minutes. Oh, it's going to be fun. This is going to be the greatest. Let's say the end of a 120 millimeter minute hand. I set up this clock at the beginning of the semester for this demonstration. Okay? See that minute hand. It's 120 millimeters. I measured it. And we're going to calculate the following. T, F, theta, omega, alpha, Vt, and AC. Everything we've talked about. Let's calculate for a minute hand. And let's do it in 1 minute. What do you say? Oh, we only have 1 minute to do this. Okay. What's the period? In seconds. 60 seconds. Is that how long it takes a minute hand? Oh, wait a minute. The minute, that's a second hand. Oh, shit. Wait, what did I do? This is the second hand. Wait. Yeah, the second hand. All my numbers are for the second hand. The period of the second hand. What's the frequency of the second hand? 1 over 60, 0.0167 hertz. Or you could put inverse seconds if you want. What's the angular position of the second hand? The current time. I don't know, right? It's moving, right? The angular position is changing all the time. So right now it's 45 degrees, depending on how you define 0 and which way is positive. What is omega? The angular velocity of the end of the second hand. I said the end because some of these are going to be translational velocities, right? Well, we have the period, so I would use, what did they ask for? I would use this idea, that omega is 2 pi over t. Right? So omega is 2 pi, goes through 2 pi radians in what? 60 seconds. All right, so blah, 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 0.105 radians per second. So you can see this is just plug and chug. You just got to realize what number means what. What's Vt? What's the actual speed of the end of that second hand? How fast is it going? We could do this. Or now that we have that one, we could do that. Now that we have omega, this is the more direct one, right? It's 2 pi. What's the radius? 0.12 meters. Over what? Over t? Yeah, over t, over 60 seconds. How fast is it going? 0.0126 meters per second. That sounds pretty slow, but meters per second is pretty fast, right? I mean, that thing is not moving anywhere near a meter in a second. It's moving a teeny bit in a second. So what's that? It's like 1.2 centimeters per second. That's believable. We could say, okay, let's do it the other way. What's Vt? It's omega r. What is omega? 0.105. And what is r? 0.12. 0.1 times 0.1 is about 0.01. Right? So sure enough, it's about the same thing. So these formulas are consistent. What do you know? What about the centripetal acceleration of something on the end? Oh, it's just v squared over r, right? So it's just this v, 0.0126 squared over 0.12. And I don't know, it's 0.00132 meters per second squared. You can check your work. Okay. So we're just plugging in. And I'll leave as an exercise for the reader this one. Plug this one in, you'll get the same thing as what I got from v squared over r, because it's the same thing. These things are not really different from each other. Okay? Okay, so what we're going to do now is take our break, and I'm going to show you one thing to look at here. And y'all can see if you know what it is. I think you're going to know what it is. Oh, no. No, no. There we go. It's not this exciting, so please talk amongst yourselves. Okay. Yeah. Okay, so anybody have a guess what this is? Yes, what is it? Yeah, let's see, I think that's the cochlea there, but what I'm guiding your eye towards, the thing relevant to us is this. Look at these three loops. That's your vestibular system, I think is the word. You have a Cartesian coordinate system in your head. Look at this. This is why we prefer Cartesian coordinates. This tube detects you doing this, and this one detects you doing this, and this one detects you doing that. And it's actually like Cartesian. That's why we like Cartesian over rotational, or spherical. That's my theory. I don't know if it's true or not. But this really is in your head, right? That's an MRI of... That's actually my... No, it's not. Rather than just look it up on the internet, I went and got an MRI, and, you know, because I'm really dedicated, and, you know. Okay, so this has all been kinematics, right? Now we got to do dynamics. Now we got to figure out what's the force that's going to cause these things to go around. Okay? And yes, everybody pointed out I didn't calculate alpha. So since it was uniform circular motion, alpha was 0. We didn't have it doing angular acceleration. And that's sort of a question of how much we're going to really cover that. We're probably going to focus on uniform circular motion. I'm going to try to get to it a little bit in the lecture, and on the homework it's unclear yet because I haven't finished the homework. Okay? All right, let's see. I can't write the homework until we do the lectures, but I can't do the lectures without writing the homework. It's like Chegg. I should start a company and take people's money so they can cheat. That's what Chegg is, chicken and the egg. A bunch of guys high in their dorm room. Dude, is it the chicken or the egg? Let's make a website about it. Okay, circular dynamics. Okay, basically all we're talking about here is a net force must cause, I'll say, AC. Right? By Newton's second law. The sum of the forces in the centripetal direction must equal the mass times the acceleration in the centripetal direction. Now things are rotating. It sounds weird, but it'll be fine. You're going to be okay. You might not be okay if you get out of your seat, though, okay? You guys in the front, let's all make eye contact. Do not get out of your seat right now, okay? Because this might hit you in the head. And I didn't register this party, so. Okay, so a conical pendulum is basically one that hangs at an angle, and then you give it a little sideways motion, it goes in a circle. Do not get up. Stay where you are. Look at that thing going in a circle. Very beautiful. It doesn't look dangerous, but you don't realize how heavy it is, right? Ow. Right? I mean, it will hit you pretty hard. There was once an unfortunate news story, really happened not too long ago, where like somebody working on a site didn't know a lot about the big balls that knocked down the building. And one was moving slow, and the person thought they could stop it. And yeah, I mean, they died. I mean, they got between it and the wall. And they just had no intuition. So things that are heavy moving, you should stay away from them. Like a car is the only exception. It has airbags in it. Okay, so conical pendulum is basically just this situation. We have this big mass hanging down, and it's going in a circle. So I got to do 3D drawings now. And then here's like the normal direction, like that. And I'm going to call this angle phi. Okay, I'm going to call it phi because theta, we've been talking about, is more like this angle going around the circle. Phi, or phi, what Chegg charges to help you cheat, is another way of saying it. I don't know what Millie's music video is, so I don't know. I don't know who Millie is. Millie is Millie Dresselhaus, who I knew. That's the only Millie I know. So we got to think about forces. Let's just think generally what's happening. Is this cable under tension? Yes, it is. I can feel it. It's like ready to snap. It's like us, right? It's under tension. So we have a tension force up, and we have like the weight pulling it down like that. Right? But how does that make it go around? We give it like an initial velocity, kind of like that. Right? If I just hold it at an angle and let it go, it doesn't go around. Right? But if I hold it at an angle and shoot it to the side, it goes around in a circle. I can make bigger circles, but I'm not going to. When I'm in here alone, we have huge circles, but I'm not here alone. Okay, so this is now dynamics. We have to think about forces and what they do, so we need a free body diagram. Right? So here it is. Here's the mass. And in these dynamic problems with something rotating, you kind of have to think about how to do your axes. If you think about it, it's moving in a way that VT keeps changing. That'll be annoying. The centripetal acceleration keeps changing. That's annoying. So you just kind of pick a snapshot. That's why I kind of drew it on the side here. So we'll say in this snapshot, we'll consider this y, and we'll call this centripetal direction. We could call it x. But I like to call it centripetal to remind you that we're not just doing xy kinematics. We're actually doing circular motion. Okay? So let's go ahead and draw it that way. mg is down. All right. And since you guys are like trig ninjas at this point, I'm going to not draw the full tension. I'm going to draw the components because we need the components, right? So there's a component of tension that way, and there's a component of tension that way. And let's say which trig identity, oh, it's this component sign. Oh, but the angle's in the wrong place. So you've got to be really good at trig now, right? So if I want this component, normally that's the cosine because it's to the side, it's the adjacent to the angle. But when it's the opposite angle, you just switch sine and cosine. So this is t sine theta. Notice how I look at my notes as I walk. Do you ever catch me when I do that? It's clearly t sine theta. Okay? Now, this one over here is clearly the opposite, is the vertical one, which is normally sine, but because we switch, it's cosine. T cosine phi also. Okay, let me stop screwing around and mess you up here. So this component is t sine phi up, or phi. T is t cosine phi. So there's our free body diagram, right? We have two opposing forces in the vertical, and we have a constant force to the right in the centripetal direction, right? So let's see what we're going to learn. Vertical. Sum of the forces in the y must equal, is it moving in the y? No, right? It's perfectly level in the y, so it must be 0. It's not accelerating in the y. So t cosine phi minus mg, the weight, equals 0. So this is how you get the tension. Right? The tension, if you want real quick, is just the weight divided by the cosine of phi. It's not times the cosine of phi. Okay? If I get this thing at a really big angle, it needs a huge tension because only the vertical component is holding it up, and the vertical component at a big angle gets really small because phi goes to 90. Okay, so now let's do the centripetal direction. This is where the excitement happens for the conical pendulum here. So there's only one force, t sine phi. And what is it equal to? The mass times the acceleration, but what is it? The centripetal acceleration. If we're in uniform circular motion, the only acceleration is the centripetal acceleration. So there it is. And also we're considering this direction, so that's the only one, is the centripetal. So you say t sine phi equals the mass, and what is the centripetal acceleration? Well, we're thinking in terms of giving it a vt. I'm sorry, we're trying to find, I didn't really say what we're trying to find. Find vt as a function of phi. That's what we're trying to do. Or get some relation between how fast it goes and how high I hang it up. Because you'll notice if I have a very small phi, this is what I forgot to say at the beginning, it's kind of a slow vt. It's hard to get it to go in a circle. Small phi, it's moving kind of slow here. If I come this way, I believe it can't possibly hit you. Not sure about that, though. Might take out my computer. And a big phi, it's moving much faster, isn't it? Oh, okay, see? That's what we're trying to find, is how does VT depend on phi? Okay, so I forgot to say that at the beginning. So let's start over. No. So we do free body diagram. Vertical gets us attention. This one is now AC, so it's VT squared over R. All right, so VT is the thing kind of we're trying to solve in terms of phi. Okay, but tension is also unknown. Between VT and phi is what we're dealing with. We know the mass, we know gravity, but we don't really know the tension, so we want to plug this in for the tension over there. There has to be two signs show up. Oh, it's VT squared. Oh, yeah. Yeah. So the tension is mg over cosine phi. mg over cosine phi times the sine of phi equals, I remember, m VT squared over, what about the radius? God, I screwed this up. I gave you the length. It's a conical pendulum of length L and mass m. I should have written this out as a problem. It's a conical pendulum of length L and mass m. You hold it at an angle phi. How fast does it go? That was supposed to be the problem that I forgot to write down. Okay, so we've gone through the whole thing. We don't know the tension. We don't know R, but we know L. And there's a triangle here. All right, so if we do our SOHCAHTOA here, we can write it all out. Sine phi is opposite R over L. And you see, oh, it's not a component. We're actually getting the short part. L is R over sine theta. Or R is L over sine theta. So we put, I'm sorry. Okay. So we have R here. mv squared over R. It's going in a circle this way. And we want to write it in terms of something we know, which is L. Right? So R is L sine theta. Thank you. L sine theta. Let's see. It's a good time to stop for a question, because I can't do trig anymore. Oh, you have no idea what's heading your way later. Okay. So we're going to solve for this. So we're going to cancel the mass. And this is just a huge bumbling way to get to VT. So we found that VT squared is what? I can't even do it anymore. G times L. All right, times what's left? Sine over cosine is tangent of phi. Good Lord. Tangent of phi. And then we bring up another sine of phi. That's actually the answer. It's not pretty. Okay. Almost worked it backwards. But that's the answer. So what this tells us is, does this increase? Is it what we expect? For a really small phi, a really small angle to the top, is it slow? And for a really big angle to the top, is it fast? Well, let's have a quick look. What we got to think about, what I want you to be able to do, what will help you do problems, is to be familiar with the shapes of your trigonometric functions. All right, so if here's phi, I could plot tangent. If I go out to 90 degrees, probably the biggest angle I'm going to make is 90 degrees. This thing will be going really fast, potentially, because the tangent looks like this. And it goes to infinity here. Oh. Right? So that term goes to infinity at 90. That's tangent. If you've never seen it before, there it is. And sine, what does sine look like? Sine is 0, and sine kind of goes like that. Right? You know what sine looks like. Okay, I must have written my tangent wrong. Will all the box equations be given on the exam? Probably, yeah. What is the L in the last equation you wrote? L was the length of the pendulum that I forgot to give at the beginning. Do you mean phi instead of theta? Yeah, I changed it, yeah. Okay, but let's think about these functions. We're multiplying sine by tangent. That's all we're doing. So what is the product of sine times tangent? Well, you know. Right, if this is still 90... So we can see if this answer makes sense. The product of sine times tangent right, is what? It starts at 0. It kind of increases together, but it still goes to infinity. Right? So if we ask ourselves, does it make sense with the world? Then yeah, it's really slow. It starts at 0 with no angle. It doesn't move at all, and it gets faster and faster. Then imagine what it would take. Now, I could do it over your heads, like if I got way back here, but I won't, right? Imagine what it would take to have this thing at like 80 degrees. It would have to be flying really fast because it would have to be able to cancel this vertical force. And as phi got really big, cosine would go to 0. Basically, there'd be very little vertical component left of the tension to cancel gravity. So the tension would have to be huge so that the little cosine component could cancel it. And if the tension is huge, then the thing goes really fast. So it makes sense. Okay, so that was just supposed to be a simple example of using a force to figure out a circular motion problem, okay, the conical pendulum. And it did something that you're going to have to be able to do in these problems, is to think a little bit in 3D. Right, we had an angle this way, and we had something going around that way. So let's look at another example of a circular motion problem. One that comes up all the time. Very common problem. Let's see. Okay, so that was a case of doing circular motion with gravity and tension. Now let's do circular motion with gravity and normal forces, because that's a little harder. And the reason is, what's the magnitude of a normal force? Whatever it takes. Right? There's no formula where we just plug it in and we're done. We got to think a little bit. So the problem we're going to do is the old how fast to stay on the loop. Right? So, you know, you've done loop things before, right? So this is like a loop track. And I've got, I had these like really fun, here they go. Yeah, here we go. So, you know, if you're like on a roller coaster and you're going to go through a loop, you're hoping you go fast enough, right? If you go too slow, oh no, now we're stuck for an hour until the 13-year-old comes and gets us down, right? And if you go a little bit faster, you might get partway up, and that's bad, right? You don't want that to happen. So you got to be going fast enough that you actually, barely made it. All right, I have another one. Fast enough that you really make it. Right? And you could almost hear it barely kept contact there. But if you go really fast, right, then you're fine. That's what you want to happen, right? So we've got to think about the forces happening right when it goes there. Okay? This may not really be a perfect circle. All kinds of things may be going wrong. But we really just care about this position. And you'll see why that simplifies it a lot later here. I can lower it. There we go. Ooh, look at that. So let's see. Let's calculate then what's going to happen. So let me draw it real fast here. Like that. And you're on the little car here. And you're on the little car here. And you're going at V. And you're going at V. But that's not the V we want. So we haven't done all the physics yet. But hopefully you could tell that you're going to lose some of this velocity when you go uphill. Right? Gravity is going to slow you down. So this isn't really the V we care about. The V we care about is how fast is it still going when you get right there. That's the VT. So the problem would say how fast to stay on the loop at the top. So I should write these problems more clearly, obviously. Right? So at the top, we're going to say this is approximately circular motion and say how fast do you stay on the loop. What does it take? The radius of the loop is R. Okay. Here we go. We're going to do this in several boards because this is some critical, crazy stuff happens. Okay. How fast do you have to go to stay on the loop? So the first thing I would do is a Freebody diagram. Right? That's usually, we're talking about forces, circular motion. We're going to use F equals ma. So we need to know the net force. So here is the object. So there's two forces on it. One is gravity. Right? It has a weight. Pretty sure even if you go through a loop, the weight is down. Even if you're upside down, the weight is still down, right? The weight doesn't care which way your head and your vestibular system is oriented. So that is down. Okay? The other force is given away with the title of the board. It's clearly a normal force. Which way is the normal force? What are we talking about normal force? It's the force between the object, or you and the seat, or whatever, between the object and the track. Or if it's you sitting in a chair, you in the seat, right? So let's think at the top, is there a normal force? And if you think, if you've done this before, you feel, yeah, the seat's still pushing on you. And which way does it push you? Down. A normal force can't pull you up. It can't lift you. A normal force only pushes you down. Like that. Okay? So that is your free body diagram. And hopefully that makes you say, this is what most people's reaction to that is, right? And that means in physics, that means whence the force. Right? How could that possibly be correct? Because look, I've got two forces pushing down and I'm not going down. I've got two forces pushing down, I'm not even moving in the y, I'm moving in the side. how could that possibly happen, right? It does happen. It totally makes sense. Because how could this be? Look at it this way. Think about the velocity in the y direction. Because we're talking about a force basically down in the y direction, or we could say the centripetal direction. But as this thing goes through here, what is its y velocity here? Well, it's pretty big, right? And then once it gets down to here, it's slowing down, so it's a little bit smaller. Once its y velocity there is 0. And then it starts to speed up again. So we're not doing this mathematically, but you could probably imagine that's what's happening, right? Its initial velocity gets turned in the y direction by the track. Big y velocity up, big y velocity down. So what's happening? The y velocity is changing, right? The y velocity is changing from up to down, so the acceleration is down. So it does accelerate down. Well, the centripetal acceleration. Okay? So that's one thing that's tricky. You know, if I just draw something and say it's circular motion and say which way is the centripetal acceleration, you say, well, it's in. Centripetal means center seeking. But in a physical problem, sometimes you lose sight of that, right? In a physical problem, if we say it's circular motion, AC is always perpendicular to VT. So that's why the forces down are what create AC, even though at that moment, it's not moving down. It's just like this, right? At the top of the trajectory, it was still accelerating down. The whole trajectory, it was accelerating down due to gravity. And at the top, it wasn't moving down, but it was accelerating down. So this is exactly the same thing, okay? So that's the hardest mental thing to get over, okay? But you're over it already, right? I can tell. Right? The cookies are ready. So now let's just write it out. Let's just do some of the forces in the centripetal direction, in this case down in y. Some of the forces centripetal is mass times acceleration in the centripetal direction. Okay. Okay. I'm going to define centripetal direction as up positive. I don't know. My notes did. I don't know. It's kind of stupid. Everything's down, but that's what I did. Okay. So what are all the forces in the centripetal direction? We already drew them. There's the normal force, which is pushing down, and there's mg, which is pushing down, and then there's the mass times the centripetal acceleration, which is down, which is vt squared over r. And since it's down, well, I'll put the negative right on it so you can definitely know. That's where the negative came from. So all the terms are negative. So I could have just pointed down positive and made them all positive. Okay? But let's think about what this really means. So when you're moving at this vt, at some tangential velocity over the top of the loop, a force mvt squared over r is needed, right, to make that happen. Right? If you're going to move, there's something has to apply a force. Right? So if you're fast, if vt is large, then what's it going to be? Weight will do something, but weight is constant. If you go too fast, weight isn't enough. Right? So if v is large, mg is not enough. Something else has to help out, and it's a normal force. Not enough, n helps. And if vt is really slow, let's see what would happen. If vt is slow, mg is too much. Right? That's the case where it doesn't make it, right? It falls off the loop before it gets there. So the magic question then was, how fast, what's the critical amount just to stay on the track? So that was a bullet, and that was a bullet, and that was a bullet. So to just stay on is when n equals 0. Remember, n is whatever it takes. If it wants to go fast, it'll give you some normal force. If it's going way too slow, it won't even bother. But the point where it just makes it is where the normal force goes to 0 right at the top. Right? It gets loose right at the top. So all you do is set that equal to 0. And you say mg equals mvt squared over r. I made all the negatives positive. Set that equal to 0, cancel the m's, and you get vt is the square root of gr. And that's how fast you have to be going at the top. Books and I and every old physicist will write all kinds of problems, variations on this. The answer is always the square root of gr. Like we can't come up with a way to make it not be the square root of GR. If you're going on top of the hill, how fast do you have to be going to not fly off? Square root of GR. Okay? It's always the square root of GR. It's annoying, but that's the way it is. Okay? Okay, so that was a case where we used normal force. So you see normal force a little trickier than tension. Right? Tension, you just know what it is. It's T. Normal force can take variable values. Let's see here. Let's do another one. What time is it? 10 minutes to do that. Let's talk about non-uniform. I have one other one, but it's trivial. I'll put it on the website or something. We drew in on the Freebody diagram, so why do we say it's 0? It wasn't 0 yet. Right? We were saying there could be a normal force there because we could go at any different kind of VT. But now you realize, we're going through a mental process to realize, oh, we want the special case where n equals 0. It depends on how fast you're going. So we went ahead and wrote it. Okay. So I just want to point out then with our final 10 minutes here that there is more than just uniform circular motion. This is the second, this is the second half. Class is almost over, right? I don't know. I forgot. Okay. What if uniform, or what if the motion is not uniform or circular? What if it's just some general motion? Are any of these values useful? Right? Can we think of things rotationally? For example, let's look at the projectile. I mean, you know this one. You've thought about it a lot. We set something off and we shoot it at V naught at some angle theta. And what does it do? Ooh, like that, except it would fall underneath there. Is there anything circular about that? Right? It's parabolic. It's a parabola. But it's circular in one place. And if you have an appreciation of symmetry, that answers the question. There's only one unique place on that trajectory, and that is at the apex, right? If it's circular here, it'd have to be circular there. If it's only circular in one place, it must be circular there. Okay? So you could argue that that is going through uniform circular motion there. So it's at the apex because that's where V is perpendicular to A. That was kind of one of the definitions. I may not have said it real clear, but one property of uniform circular motion as it goes around is that V is tangential, A is radial, in. They're always perpendicular to each other. So when you're here, there's V and there's G. Or there's A, right? It's acceleration due to gravity. So they aren't perpendicular. And when you're here, there's V and there's G, or A. Not perpendicular. But the special part is right at the apex, your V is completely sideways. And your A is completely down, right? AY. I'm sorry, I changed the label every time. There we go, AY. So we could say then that AC, the centripetal acceleration, basically just equals G at that point, at the apex. So who cares, right? I forgot why we care about this. Let's see. So what you could do then is you could have a point and you could inscribe a circle in it and say, well, you know, it's kind of like circular motion at this point. Who cares? We probably won't have time to get to. But let me give you an example of, like, let's do a calculation with this. Let's do something fun here. N is, Somebody asked, is N 0 when the ball falls off the track? No. N is undefined because the ball's not touching the track. So there is no N. It goes to 0 and then it doesn't exist anymore. So you can decide if not existing means 0. This isn't a philosophy class. So what we could say here, the fun question I want to drive is so say you're given the standard trajectory, V naught at theta, right? So the standard situation, V naught at theta, is H or D larger. And what does that mean? By H, I mean the height. All right, the height of the trajectory, which we have a formula for. And what is D? The diameter. 2 times the radius. of the circular motion happening there, even though it's not a circle. So what I want to show you is how to think about how to get that that radius. Like one problem might say, what's the radius of the motion here? It might be infinity. It might be 0. So let's look at that real quick. So h you would look up. In your notes, you could do this on the pledge problem. We know it's v naught squared sine squared theta over 2g. Right? Straight from our other derivations. But how are we going to get the radius of this circle? Well, if at that moment it's uniform circular motion, then we know that, why is there a 2 there? Oh, I multiplied by a 2. Okay, yeah. We know that the sum of the forces equals MAC, right? So we know that the sum of the forces in C equals the mass times acceleration in the centripetal direction. So we say at this moment it's circular, so we say this equals mass times G, because G is a centripetal acceleration. And then, I'm sorry, no. Right. The force is mg and equals mv squared over r. That's what we have to say. There we go. That's what I'm trying to do. And then we would cancel the masses. All right. And then we would say, let's put a 2 here and a 2, or let's say a half to get a 2 down here. And then what v is that? We've got to realize, wait, that's not this v. It's this vx component. Vx component like that. Okay. Yeah. Let's get rid of this. Okay, I screwed this derivation up, so let me put this away. I put a 2 in the wrong place. So let's see if we're all together here. The centripetal force is the force that's driving into the circle is mg. We know that's equal to mv squared over r, and we know it's vx, right? So we cancel the m's. We got g, and what is vx? Fortunately, vx is constant, right? So we're combining the stuff we learned before to this. It's v naught cosine theta equals v naught squared cosine squared theta over r. So we just replace the r and the g like that. But the diameter is 2d, is 2r, right? So d is 2 v naught squared cosine squared theta over g. So we say, which one is bigger? Oh, then you would just plug in your numbers and say which one is bigger. But you can kind of tell that if you're at a low angle, if theta is small, cosine is 1 and sine is teeny. So that's going to make the circle is going to be bigger if you're like that. See, then the height is small and the circle is huge. If you have something like this, then the height is big and the circle is small if theta is big. Okay? So it kind of makes sense. So I think I put that one in there as an example of how we could combine different parts of the class, right? That'd be a good exam problem where we say, here's circular motion and a projectile, and let's combine the two numbers. So let me answer a few of these. I'll shout these out. There's only one. Why are h and d not the same? Yes, that's the point. Why are h and d not the same? Is there different things? We're looking for different things. One was the height of the parabola, and one was the diameter of this circle. We're just trying to compare them for fun. What a disaster.